Hello everyone, welcome to the course on digital signal processing. This is lecture 4 and in this lecture we will see the designing of the Chebyshev filters. So as in our last lecture we have seen that the IR filters are classified as the Butterworth filter and the second one is the Chebyshev filter. So Butterworth filters having a response, we can say the maximally flat type of pass band as well as it is a maximally flat in the stop band, whereas we have the different type of filter here which is known as Chebyshev filter, which is having the ripples in the pass band, whereas it is maximally flat in the stop band. So here we can see this is the pass band, and in the pass band there are the ripples, and in the stop band area we can see that the filter is a maximally flat type of filter. So we have a maximally flat response in the stop band, whereas in the Butterworth we have both pass band and the stop band having a maximally flat type of response. So we have the magnitude response over here, and the magnitude response having a EQ ripples in the pass band and the maximally flat type of stop band. So by increasing the order, as we are already aware that as the filter order increases, so the response, the magnitude response approaches towards the ideal kind of response. So as the filter order n increases, the Chebyshev response approximates the ideal response. If we talk about the phase response of the Chebyshev filter, then more non-linearity. So as we are increasing the filter order, we can say that the phase response become more non-linear as compared to the phase response of a Butterworth filter. Now, let's say we have the magnitude response given by mod of h of omega. We are having the cutoff frequency, and we have A is known as the filter gain, and epsilon we are called as a constant, and ohm c which is called as a 3 dB cutoff frequency, means at this particular frequency the gain reduces to 1 by root 2 times the maximum value, whereas the Cnx, this is nothing but the Chebyshev polynomial of first kind, and the order is nth order. So Cnx, the general we can say the representation for the Chebyshev polynomial is given as Cn of x, where it depends on the value of x. If mod of x is less than equal to 1, so it can be written as cos of n cos inverse x, whereas if mod of x is greater than 1, then this will be converted to a hyperfunction, so cos of n and cos hyper inverse of x. So we have the that was the representation for the Chebyshev polynomial. Now if we'll see the design aspects of the Chebyshev filter, so as per the requirement, we have the response, we have the magnitude response, we have the attenuation delta 1 and delta 2. So delta 1 we can say the attenuation up to a certain frequency which is omega 1, and delta 2 the frequency which is beyond omega 2 to pi. So this is nothing but the digital frequency specifications of a low pass filter. So we just want to basically derive some results. On the basis of that, we'll be able to design the Chebyshev filter. So let's say initially we assume that our gain A is 1, and we just put these values delta 1 in our last equation, which is equation number 1. So we have delta 1 square is less than or equals to, we have this particular factor, this is a magnitude response, and this will be less than 1. And from the second equation, we have the equation which correlates the attenuation in the stop band. So we'll be utilizing both the equations to basically calculate the order of a Chebyshev filter. So in the next step we can see that if we assume the cutoff frequency ohm c which is nearly equals to ohm 1, so we have the Chebyshev polynomial Cn ohm c divided by ohm c, which is nothing but Cn of 1. and the value of Cn of 1 is equal to 1. So definitely we'll be utilizing this value of the Chebyshev polynomial at let's say value 1. So from our last equation we can say that delta 1 square is less than equals to 1 by epsilon square, and we can calculate the value of epsilon, which is a constant. So now if we compute ohm 2 by ohm 1, so we have Cn of ohm 2 by ohm 1, which will be greater than, definitely greater than this particular factor. And since we are aware that ohm 2 is the frequency correspond to stop band, whereas ohm 1 is the frequency correspond to the pass band, so definitely ohm 2 is greater than ohm 1. So what we have this quantity ohm 2 by ohm 1 greater than 1. So this quantity is greater than 1, so definitely it can be written as cos of hyper n cos h inverse of ohm 2 by ohm 1 will be greater than equals to the entire factor right hand side is exactly same. So if we'll try to calculate the value of n from this first equation, so I'll be having a relationship which will be n greater than equals to cos hyper inverse 1 by, also in this particular, instead of this factor 1 by epsilon, I can replace this value. So the formula will be bit similar what we achieved in the case of Butterworth filter. If I can write down the formula for calculating the order of the Butterworth filter, it has to be something like this. Here we have log of these attenuation factors 1 by greater to square minus 1 by delta 1 square minus 1, and also divide by log of ohm 2 by ohm 1. So we can clearly see over here that here we have a factor of 1 by 2 outside. Clearly we can see that both the equations are used to calculate the order of the filters. So here this will give you the order of a Chebyshev filter, whereas this one will give you the order of the Butterworth filter. So there is a bit of the similarity between both the relations. Here we have the log, and here we have the cosine functions. Now, so on the basis of that, if the filter is having a order even, or we achieve the filter order as odd, so on the basis of that I can write down the transfer function of the analog filter or the analog prototype filter, which can be written as either this is equation number 2, this is for n is even, whereas this equation number 3 is used when the filter order is odd. So on the basis of our last equation, we can write down that which transfer function is suits for our Chebyshev filter. Now this equation is quite same. We have already used somewhere in Butterworth designing 2 times of yn sine 2k minus 1 pi divided by 2n. Also we have the equation for ck and c naught equals to yn. So these all equations are very, very helpful in writing the overall transfer function of a Chebyshev filter. Now this yn again depends upon this epsilon factor, and the parameter bk can also be obtained from this equation, or we can say a can be obtained with the help of again bk. So we'll be having, let's say we have k equals to 1, k equal to 0 to n minus 1 by 2. So we can utilize both the formulas when n is even or n is odd. So these are the design steps. So first of all, we have the specifications, digital frequency specifications of a low pass filter mentioned, and we need to utilize a bilinear transformation by assuming t equals to 1. So as we can see that from this digital frequency specifications, that we have 0.707 is the attenuation in the pass band, whereas 0.1 is the attenuation in the stop band. So clearly we are already aware that this is nothing but delta 1 this is nothing but delta 2. Also, this is omega 1 and this one is omega 2. So these are clear from this particular specifications. Also, there is a quite important thing that the definition for the cutoff frequency, it is the when the gain reaches 1 by root 2. So 1 by root 2 is nothing but it's around 0.707. So definitely this delta 1 is means corresponding to this particular attenuation, we have the frequency 0.2 pi. So this is nothing but equivalent to the cutoff frequency also. So this will become a bit easier to solve the cutoff frequency of the Chebyshev filter. So in the next step, yeah. So we have delta 1 0.707. We have the attenuation in the stop band. We have the attenuation of we have the frequency, pass band frequency, and we have the stop band frequency. So clearly we can say that the ohm C, which is the cutoff frequency, is equal to ohm 1, and we have to utilize the bilinear transformation. So this is the equation used to transform the digital frequency into the analog one, 2 by t tan of omega 1 by 2. So on the basis of that, I can calculate the cutoff frequency, analog cutoff frequency. Similarly, ohm 2 can be calculated as, again we are using the BLT, bilinear transformation, and the value comes out to be 2. So therefore we are interested in finding the ratio which is ohm 2 by ohm 1, because that will decide that what type of Chebyshev polynomial will be used over here. So if we put ohm 2 by ohm 1, so ohm 2 is 2 divided by 0.64. So definitely this value is greater than 1. So once this value is greater than 1, so definitely the formula which is used to calculate the order will be somewhat in terms of cos hyper inverse function. Otherwise it is nothing but cos function. So before starting with the calculation of order, I can compute the value of epsilon. So we'll be utilizing over here the value of epsilon, and we just calculate the order is 1.669. So as we are already aware, the order of the digital filter of this particular prototype filter can't be a decimal value. It has to be an integer next to that particular decimal value, which is 2. 1.669 can't be used, and we assume that the filter order is 2. Now, since the filter order is even, so if n is even, so we can decide what type of transfer function can be used for the Chebyshev filter. So we have, this is pi k equal to 1 to n by 2, and also we have bk ohm c square, and we have the factor in the denominator. Just put the value of n. So we have only a single factor, which is b1 ohm c square divided by s square plus b1 ohm cs plus c1 ohm c square. Now we are interested in finding the values of these constants like b1, like c1, and capital V1. So we utilize those equations in terms of yn, and similarly with the help of yn, which is only y1 over here, I can calculate n equals to 1 and 2. So we have two values, y1 and y2. So we have b1 over here and we have c1 over here. Now we just want to put these values to calculate the value of bk. bk means capital B1. So with the help of this b1 by c1, I'll be having the value of b1 0.5. So these values can be utilized. b1 over here, again we have a small c1 and we have a small b1. All three values can be used over here to get the overall analog prototype transfer function. Now, yeah, we can clearly see over here, I'll be having HS, the transfer function. Now we want to basically convert this analog prototype low pass filter into its corresponding digital filter, and the method we need to use is bilinear transformation. So we must be aware that analog filter can be transformed to a digital filter Hs can be converted to Hz if we'll substitute S equals to 2 by T 1 minus Z inverse divided by 1 plus Z inverse. Also we can put 2 by T Z minus 1 divided by Z plus 1. Both are the same equations. So we just put the value as the value of S in our last transfer function, and I can further simplify this the system function. So I'll be having Hz. This is the system function for the low pass filter. And further, if you want to realize this filter, let's say this is IR filter, if you want to realize using direct form 1, direct form 2, easily we'll be able to realize this. So these are the steps behind the design of a Chebyshev filter. So this one was Chebyshev type 1 filter, or it is also called as Chebyshev filter. There we are having a different type of filter which is called as Chebyshev type 2. So in the Chebyshev type 2, what kind of response we have? We can see that we have the maximally flat kind of response in the pass band, whereas we have the ripples present in the stop band. So this type of filter is also known as inverse Chebyshev filters, because the response in the pass band and the stop band is bit opposite. So now we are moving towards the different topic which is called as a frequency transformation. So frequency transformation, basically what happened throughout the designing of IR filters, we were basically interested in designing the analog low pass transfer function of a filter. So once we are having the low pass transfer function, but let's say being a designer, if someone asks you to design a digital filter which is a high pass, or it's a band pass, or it's a band reject filter, so we need to use the transform kind of approach. So we'll be utilizing the frequency transformation, and we can convert that prototype low pass filter into the corresponding high pass filter, band pass filter, or band reject filter. So we can say that basically we have 4 different type of filter. We are already aware. We have low pass filter, we have high pass filter, we have band pass filter, and we have band stop filter. So in the design technique, so far we have discussed, we are only designing a low pass filter, and that low pass filter is nothing but known as the prototype, analog prototype low pass filter, or the system function Hz. So if a high pass or a band pass or a band reject filter need to be designed, then we'll be utilizing the approach which is called as frequency transformation approach. Now the next question over here is that what are the types of frequency transformation? So frequency transformation can be done in both the domains, in the analog domain as well in the digital domain. So first of all, we have the analog frequency transformation. So analog frequency transformation, and the second one is called as a digital frequency transformation. So let us see what is the approach behind the analog frequency transformation. So in this type of transformation, the analog system function which is called as a prototype transfer function HPS is converted into the corresponding analog system function HS of the desired filter. Let's say if we want to design the high pass filter, so I'll be using some transformation formulas, but that are corresponding to analog domain. Means if we have HPS, so I can design HS for a low for a high pass, for a band pass, and for a band reject kind of a filter. But both the filters are in analog domain. So that's why this kind of approach is known as analog frequency transformation. Afterwards, since we are already aware that we are interested in designing a digital filter, so definitely at this particular stage, we are using the certain kind of a mapping technique. It can be a impulse invariance transformation technique, or it can be a bilinear transformation technique. So this is a method behind the designing of other filters, which is high pass, band pass, and band reject. The other kind of approach over here is called as a digital frequency transformation. So what happened in this? Initially what we have the prototype low pass transfer function. Now this analog low pass filter transformation function is further processed, and it will be converted to the corresponding digital low pass. It will be converted to a prototype digital low pass system function HPZ by using certain transformation technique called as IIT, which is impulse invariance transformation, and the second approach is BLT, bilinear transformation. Afterwards, since we are getting a filter now, since we are getting a digital filter, here both the filters are LPF, low pass filters. But being a designer, we are interested in designing the high pass, band pass, or band reject. So now at this particular stage, we are basically doing the transformation, frequency transformation. But here we are in Z domain, and here also the filter was in Z domain. So this kind of transformation is called as digital frequency transformation. So we have both the approaches, and we have certain formulas that basically convert a prototype low pass filter, or we can say that analog prototype low pass filter into some analog band pass, analog high pass, or analog band reject type of filters. So we use these both the techniques. Now let's say if we'll discuss further the analog frequency transformation. So this frequency transformation used to convert a prototype low pass filter into a low pass with a different cutoff frequency, or high pass, or band stop or band reject, where OMC is called as a cutoff frequency of the prototype low pass filter, and OMC star is a cutoff frequency of new low pass filter, or high pass, or certainly OM1, OM2 are the frequency for band pass and band reject filters or band stop filters. So we have these certain formulas: low pass to a new low pass filter. Further, this low pass to a high pass filter, low pass to band pass filter, and low pass to band stop or band reject filters. These formulas need to be remembered if you want to design some band pass or band stop or high pass filters. Along with these, we have some formulas for the quality factors and the center frequency, which is denoted by ohm naught, which is under root of ohm1 multiplied by ohm2. These are used for both the filters, band pass and band stop filters. Now we have the digital frequency transformation. So as we have the analog frequency transformation, so frequency transformation is also possible in the digital domain. The frequency transformation is done in the digital domain by replacing certain variables with the help of Z inverse. We are already aware what are the different type of transformation techniques, but the point need to be remembered is that stability must be, we need to basically parallelly check the stability of the system. These are the relationships for the digital frequency transformation, like digital low pass to a digital low pass at some other frequency. Similarly for high pass, for band pass, and similarly for band stop filter. So these for certain results need to be remembered if you want to design these filters. Now there are some key points. The frequency transformation can be accomplished in any of the two techniques. However, caution must be taken in while we are using these. For example, impulse invariance transformation is not suitable for high pass. We are already aware because the mapping was many to 1. So for band pass, high pass, band pass, whose resonant frequencies are higher. So in such case, a low pass prototype filter is converted to a high pass filter using the analog frequency transformation approach. So this will result in a aliasing kind of a problem. We are already aware the impulse invariance transformation is having a disadvantage which is called as aliasing. Similarly, if the same prototype filter is first transformed into digital domain with the help of IIT and later converted to a high pass filter using the digital frequency transformation, then it will not have any kind of aliasing problem. So these key points we need to remember. Whenever the binary transformation is used, it is of no significance whether analog frequency transformation we are using first or we are using the digital frequency transformation first. So these are the certain key points behind the transformation. These are the references. Thank you.